I'm Sam Wayne. I'm calling from Harper Adams University over in the UK. What I'd like to share with you is some of the lessons and some of the projects that we have gone through at Harper Adams University, particularly with regard to large-scale mechatronic implementation in agriculture. So it's going to be an overview of our philosophy of agriculture and some of the lessons that we've learned along the way. So I hope you enjoy the ride. So one big question that we get in agriculture or with anybody who's dealing with robotics is, aren't we just trying to take jobs away? We see that as a knee-jerk reaction to robotics, but what we see is that technology really is a natural progression. So originally we had the plough, which removed the need for so many people digging by hand. The plough was replaced by the tractor, which replaced the use of animals and the need for animals. And eventually the tractor will be replaced by the self-driving tractor or the small robot tractor. And I'll explain why we're very keen on small robotics in a little while. But all of the time we see that as a natural progression of evolution. We're not trying to get rid of people. It is just a natural progression of technology which allows us to make better use of the land, to feed the people who need it. And really, we find that robotics hasn't displaced labour, although on the surface it might seem to, but those people who are no longer doing that particular job because the robot's done it will do a similar job. They might look after the robot, or they might do something which is a bit more mind intensive, something that's a bit more suited to a human being. So with our agricultural engineering, we have 5 main goals or imperatives that we're trying to solve. We're trying to balance supply and demand for the future. We're addressing the threat of the volatility of the food system. That means if the food runs out, how do we store it? So what are the best ways of protecting our future and making sure that people can eat? We would like to end hunger. So that means making more efficient use of the land, making sure that that land is being used to grow crops that people can eat, and that food is protein and carbohydrate rich. We have some big challenges, the challenges of meeting the low emission world. We all know about the issues with fossil fuels. And we want to maintain biodiversity. The English landscape is particularly unique in that it has a multitude of different field systems, a patchwork of different fields with hedges in between. And we're aware that those hedgerows contain a diverse range of animals which are all beneficial to the pollination of different types of foods. So we don't want to reduce that, get rid of the hedges and make large fields. We're very interested in keeping our biodiversity, which includes lakes and local habitats. So we've got a lot of challenges ahead. It's been predicted that the world will need 70% more food. That's because the population is growing. It's expected to exceed 9 billion by 2050. The population in different countries are also becoming more aware of the food that they can eat. So people's diets in the less developed countries are changing to more developed diets, more protein-rich diets as well. There'll be a reduction in the availability of labour. People are not interested in working the land anymore. People are generally interested in working in offices, on computers, electronics. So gone are the days where the whole workforce would be out helping on the land. The current agricultural revolution will happen very quickly. We believe that it's going to hit a knee point and then it will just happen extremely fast, which means that all those who haven't embraced a new technology will suddenly find themselves left behind. So we believe that the AI informed and digital connected farm will revolution the way that farmers work. Communication between sensors, agricultural markets, banks, contractors, etc., will happen automatically. So there's a huge opportunity for agri-tech. So what I'll do is I'll just explain, I'll take 4 of our projects and then I'll explain one of them in a little bit more depth and talk to you about the philosophy of them. So our first project I'd like to talk to you about is robotics and automation for soil resilience. I'm a principal investigator on that. And there is a new incentive in the government to report on the biodiversity and the carbon sequestration within fields, and there's a monetary value attached to that. So this project is to automatically measure the soil at half-meter intervals throughout many fields and continuously report on the biodiversity and the health of the soil. And farmers will get a monetary reward for having more healthy soils. These can change quite quickly, so we're looking at an automated system, a mobile robot, which can continuously take measurements in many fields and then build up a map of biodiversity. Another one I want to talk about is dynamic depth control. So when ploughing, we are ploughing to get rid of large stones, and we're trying to produce a fine soil. But what we want to control is the depth of the plough, because if we're ploughing too deep, we're bringing up too many deep stones, and the fine soil might be too much. So we want to control the depth of a plough so it is just producing enough soil depth which is needed to plant the crops. If we're ploughing too deep, there's a cost in fuel efficiency on the tractor, and also the problem that we might break and implement. The insect feeder project is to look at the intake of chickens, egg-laying chickens. So currently, chickens are fed on soya. The soya is grown and imported mostly from the USA. So it's a non-sustainable input to the chickens. Now there is a grub called black soldier fly which can be distributed to the chickens, and it's a protein rich. It can be grown in the UK. It won't proliferate in the UK. It needs to be a particularly hot environment. So the distribution of this black soldier fly is something that we're looking at from a mechatronic perspective, because the grubs can be quite difficult to deal with and distribute. And then the hands-free farm. So that builds up on the success of the hands-free hectare. It was a purely autonomous farm, and now we have a farm which is a 35-hectare farmland at Harper Adams, which is to be completely robotically farmed. Some of the other incentives that we've got here in the UK is, I'll just mention, is UK RAS. This is a wonderful resource. It's a government-funded resource, and recently I've just had a white paper published along with some other colleagues in a variety of universities, and we look at particular aspects of the application of robotics. There's a recent white paper that I've published which is looking at the training in the agri-food sector and what training will be needed for people to be able to cope with the new rise of technology. So that's a good website to have a look at, ukras.org.uk, and then you can download white papers for absolutely free. Another project we've got at Harper Adams is an agri-living lab. We have a hectare of land, and the land is to be completely covered in sensors and sensor systems and communication systems. This lab idea is to promote the use of technology in growing foods. And the idea of the agri-living lab is that farmers and technologists can come together and see the technology in action. So the technologists can understand what the farmers' needs are, and the farmers can see the technology in action and how it can improve the health. So the idea of the living lab is a good way of bringing together researchers and the users as well. So I'll just talk a little bit about the philosophy that we have on farming and why are we interested in having small light vehicles when tractors seem to be getting larger and larger. Well, the reason why a tractor is getting larger and larger is because one person needs to plough a larger amount of land by themselves. So to plough a larger amount of land, you need more horsepower. To provide more horsepower, you need a larger tractor. But a larger tractor is more likely to damage the soil by its wheels digging into the soil and churning up. So it's actually doing a lot of damage, which then you have to undo by ploughing. So it's a self-fulfilling prophecy, especially when there's a bit of rain. So as you can see here, tractors can get stuck and absolutely decimate the soil substructure. And really, it's the soil, it's the first 20 centimeters of the soil which are full of life and nematodes and carbon and nutrients, which are giving the plants the required nutrients in order to live and thrive, which we then eat. So a project we started back in about 2015 was to get small light tractors. So this is a lawn mowing tractor, and you can see some students at the left-hand side. They are master students who made this tractor radio controlled. So the first step is to make it radio controlled and show that it's dexterous. And then the step after that would be then to put on a computer system to make it drive around autonomously. And the whole idea of having no driver on the tractor is to reduce the weight. So you can see that if a person steps on a field, you've got a very flooded footprint. This is on the grass just down below. The field here is at what we call soil capacity. In other words, it can't take any more water. Whereas the tire track from that tractor hardly makes an indentation in the ground. So it's not damaging the ground as much because its mass is distributed over 4 low pressure tires, and there's the reduced weight of the driver. So taking this project a step further, some colleagues at Harper Adams made a field which was exclusively farmed by robots. Now, the people who made this project were extremely good at publicity and social media. So what they did was they really pushed the fact that there was no humans allowed in the field and that they were going to grow a hectare of crop completely autonomously. And that was the bit that really grabbed the headlines. Now, the technology behind all of this was actually very, very simple. So the students used, and the researchers, they used the ArduPilot system. So this is something you can get quite cheaply to fly drones. And what they did was they put an ArduPilot system onto a tractor, and then they put it onto a combine harvester, and they demonstrated that it could drive the vehicle. So we can see video of this driving along. Now, I wasn't involved in this project because it was very simplified. It didn't really use robotics. What they used was to take motors and put them in place of the steering, and a motor in place of the gas pedal to change the speed of the tractor. And it's simply an ArduPilot system, which is using Mission Planner to navigate its way around. It's very limited in that it thinks it's a flying drone. It can't do anything else. So if there's obstacles in the way, it can't do dynamic obstacle avoidance. It can't test if its fuel is low and do something about it. It is purely navigating. But there was a good lesson to be learned from this, in that really most of the problems of technology is convincing the general public that it will work, and the general public is not interested in the technology behind it. They are just interested in what actually happens. So it was an interesting lesson that my approach would be to use robot operating system and to have the whole system with laser scanners for object identification and path planning, etc. But that takes a long time. This was built up in less than a year in order to use the crop to go with the growing cycle, and it really took the world by storm. So the system was very simple. It had many limitations. I, as an engineer, only saw those limitations, but the public were convinced that robots could farm. And you can see here that the impact was amazing publicity as well. And from that publicity, they could then go on to apply for more research grants and make more complicated tractor systems. So this is the next generation. They've moved away from ArduPilot, but they did use a company which created the auto steer system. And the company was Trimble. And this, you can see that there's two autonomous vehicles working side by side. So they're in constant communication with each other. And you can see that, yeah, it does work, and they've got more outputs. One of their philosophies was, how can we get around the legislation? So there was legislation which was really forbidding the use of autonomous tractors, forbidding the use because of health and safety concerns. So what they did was, rather than putting lots of safety systems onto the tractor, they built a big fence around the area. And their philosophy was, well, let's do it now and apologize if we've made any mistakes later. And we found that really legislation can be changed by doing things anyway. If the public are on your side and enough people see it actually happening, then that can be a good springboard for changing legislation. So rather than waiting for legislation to change and then doing it, get the public on board and get the legislation changed by sheer publicity. So that project has gone further. So the CAV stands for Connected Autonomous Vehicles Project, and that is now taken to a tractor that can drive itself from a machinery stall down the road and into the hands-free hectare field. So you can see a short video of this vehicle moving. Again, this is using a third-party hardware and software to drive. It's using GPS points to drive around. It has RFID connections to the barriers, which raise and lower, and now it has a laser scanner as a safety system. So if there's a person in the way, it slows and then stops the tractor, and then when the person is out of the way, the tractor carries on. And it's all built up in layers of safety which stop the tractor, a layer of GPS coordinate following, and a layer of the implement activation. So each one is a separate system with communications to the system below it. And you can see that that can now enter the hands-free hectare field by itself. Incidentally, this field is now our agri-living lab, which I mentioned before. So we've now connected it up. Something that we're very proud of at Harper Adams is we're involved, and we've collaborated with a company called Spray Drone. And the drones are from XAG in China. And we're actually running the country's first spray drone pilot course. So you can learn to spray and pilot a drone at the same time. Now, current legislation stops us spraying chemicals and glyphosates from a drone in our country. However, it's not stopping us spraying water, so we can test it out with water. We can test spraying indoors as well. We have a large soil hall where we can test that out. And we can also release seeds, so we can send seeds into environments which are very difficult to seed. So, for example, on mountainsides, etc. So that's something that's currently being used. I've just gone through the drone pilot training as well, and it's a useful qualification to have. So one of my other lessons that I'd just like to share with you is something that we learned from developing a robot. This is a robot called Ceres, and one of my colleagues called Anton Bautista, who's in the Philippines, helped us develop this robot. Now, the robot has an Arduino Uno, a Raspberry Pi 3, and it's using ROS1. What I've learned is, don't try and keep abreast of technology. If you put technology onto a robot, by the time it's connected up, it'll be out of date. So don't be shy that your technology is quite old, because technology moves faster than we can actually build devices. So take something that works, even if the technology seems to be a bit outdated. If it works, keep it. It can always be updated in the future. But trying to keep abreast of software and hardware, if you try doing that, you won't build anything. So at one point you have to say, right, we're sticking with this technology, and that's the technology that we will use. So many of you might be thinking of mechatronics and robotics and how can we make an impact in agriculture? Well, the bit that I'd like to get across to you in the next few slides is that machines can be very simple and they can do very simple tasks, and that can save the farmer and the public a lot of money and a lot of effort. So for example, if you have a spray machine, if it gets windy, then a driver has to stop spraying and then go home. But if you have a robot which is spraying, well, it can sense that when it's windy. If it's too windy, it can stop. If the wind dies down, it could be at any time, day or night. When the environment is right, it could continue to spray. So it will just sit and wait rather than having to rely on a driver waking up. I'll also talk about spray only where crop is needed as well, and that's spot spraying. If we have robots which can very accurately place items, we can have smaller robots working in swarms so they can cover a field quickly in the time that's needed. If we use very accurate GPS, we know exactly the location of where the seeds are planted. When the seeds grow, we also get weeds. Now those weeds are in places where the seeds were not planted. So it's a very simple task to make a automated device which can weed without needing to recognize those weeds. It just needs to weed where it knows no proper seed has been planted. So in this example, it's doing inter-row and intra-row hoeing because of the accurate placing of the seeds. Something that's been developed over in Scandinavia is Farm Droid. Now in the UK we have about 80 of these farm droids. They're solar powered. It's a very simple robot, and what it does is it very accurately places the seed. It's a very clever device because although it's a very simple and it's just moving up and down a field in accurate locations, it can also be teleoperated if it gets stuck. So the company which build the farm droid have the ability to monitor how a farm droid is doing, and if it gets stuck, then they can teleoperate in to the robot and unstick it. So one of the main philosophies of this robot is to have something that the farmer doesn't have to keep going out to every couple of hours because maybe a clod of earth has got stuck in one of their implements. So you can see here that it's hoeing in between the seeds. It doesn't actually recognize the weeds. It's just hoeing in between every seed which has been planted. It knows the location of every seed that's been planted because it has a very accurate RTK GPS and it planted the seeds itself. So it's doing intra-row and inter-row hoeing as it drives along. At the end of the field, it turns around and comes back the other way, and it just spends its entire days just doing it. So robotics is a very practical subject, and we can't do everything through emulation. So many times when we're developing robots for agriculture, we have to run it over and over. And really, this is the boring bit. This isn't what we were bred to do as engineers, but unfortunately, this is part of getting a robot out into market. There will be times we have to run the robot many, many times and assessing data of how it ran until we can work out why did it fail. It might only fail once every 50 times, but if it's failing, then it's not going to be good in a market. So multiple testing is something that needs to be looked at and needs to be factored into any robotics project. You can't build a robot and then leave it for the customer to test because they won't be interested. Once it breaks, then it's broken, and the customer has lost their patience with the robot. Another project we've worked on is strawberry picking. So what this robot will do is recognize strawberries, and it will only pick the strawberries which are ripe. So we can see a video of it in operation here. So it's a mobile robot with a robot arm, autonomously recognizes the ripe strawberries. But what it also does is if there's any strawberries which are not ripe for picking, it won't pick them, but it will make a record of where they are. So it will tag the GPS coordinate of the strawberries which are not ripe for picking. And then in its database, it knows where they are, and it can come back a few weeks later and then pick those ripe strawberries as well. It can also work right through the night, and it will treat them a bit more carefully than this. The gripper was developed so the strawberry was never actually touched. So only the stem of the strawberry was touched, and the gripper has a special cutting mechanism in it, so it both grasps and cuts the peduncle of the strawberry at the same time. We tested this many times. So these strawberries are not real strawberries. They're actually on a little magnetic base, but it does work with real strawberries as well. But we had to make sure that it would only pick the ripe strawberries, and many iterations had to occur. Now, we deal a lot with businesses and different companies, and something that struck me is that not every company has every expertise of engineering. So I know of a company that are trying to develop something which is mechatronic. They don't have any mechatronic engineers. So I know that there is a definite need for mechatronics engineers in the world. There seems to be a definite shortage of them. And I think that mechatronics engineers are something that can be used as consultancy, because a business might only need a mechatronics engineer at certain parts of its project or product development. So there are companies that want to come to our universities to learn the basis of mechatronics so they can develop new components and new projects, for example. So I think that's something worth considering. How can we address that situation? I don't have the answers. Another project that we've worked on is a weed recognition and microspray only those weeds. So if we had a robot system that can recognize the weeds, it could microspray them. What we've done is we've worked with a company that needed the use of weed recognition, and we used a deep learning system which was based on the NVIDIA Jetson, which recognized dock leaves in grass. And it's quite incredible how it works, because it's hard to see dock leaves. They're a particular invasive weed in the UK. They are green, the grass is green, but we found that the AI system was very accurate in recognizing this particular dock leaf. We then put it onto this autonomous mowing robot and used the spot spraying system. Another system we've used for treating of weeds is a purely organic system which recognizes the weeds by lighting them up and then attacks them with a laser. So I'll show you a short video of this in operation as well. So what we've got is lettuce, which is a high value crop. In between the lettuce, we have the weeds, and the weeds are being recognized by the system. At the top, you can see the cartoon image of the lettuce, and the laser is on a gimbal, which is just burning the weeds which are very close to crop. And what we do is we treat the weeds which are outside of that region by a small amount of spraying. And the idea is that there is no spray which goes onto the crop, and the weeds which are close to the crop are only treated by laser. So something that I'm very passionate about is the idea of mechatronics education. So I've developed this robot which I'm speaking about in the conference, and my belief is that a robot system should be very easy to set up. So you should be able to get it out of a cupboard, switch it on straight away. So I've made it battery powered. It sits on the tabletop and it's accessible. I also believe that people don't want to necessarily learn about how to interface sensors or how to drive a motor. So I believe that we should provide lots of libraries which allow people to access more complex sensors without having to learn exactly how they work, then the focus can be on developing the algorithm for the self-navigating robot and to do higher level tasks. So thank you very much for listening. My contact details are below, and I wish you all a very good conference. Thank you.